Okay, all right. Let's start. Okay, soon. You guys are in the right class, right? Advanced Analog Circuit Design, correct? Okay, so just a brief introduction. Okay, I'm Dr. Lian. My degree background is actually mechatronics engineering, and then I skipped my master. I went to for PhD. So the PhD background is exactly this course, analog IC design. Okay, so my PhD work is about designing RF energy harvester. So it will be a very small chip that can harvest the ambient radio frequency to power up low power IoT devices. Okay, so you guys are year 3 students, right? Or year 3, right? But from different intakes, I guess. There are 2 intakes here, maybe. Okay, so before we start, let's just roughly know your names. Okay. Okay, before that. Okay, so in my class, basically you can do anything you want. Okay, can you guys try not to sit so far so that I will keep trying to talk louder to the back. I won't eat you guys. I won't walk around, so you can just sit still. Next time, please try to sit in front a bit, okay? Because I don't want to, we got only 15 of you, I don't want to talk so loud. Okay, so in this class, basically you can do anything you want. I believe you guys come here to learn something if you want. If you don't want, I cannot force you. You can be physically here, but mentally not here. Okay, so I won't enforce attendance too much, but for this course, it's better for you to come and learn physically because the equations are hard. Okay, so just a quick heads up, this module is not easy. Okay, it should be a very hard module, and I think you guys know that semiconductor is the trend now. So about analog, semiconductor, VRSI, Verilog, all those are the trend now that you should know for engineering rank, except for petroleum, I guess. The field of semiconductor should be the one with higher salary. Okay, so please, if you want to learn, just stay. If not, just to let you know, this is not easy. Okay. Okay, so basically I say you can do anything you want. If you really need attendance and you don't want to attend, you cannot at all, you are not interested. My only allowable point is you have to submit everything, because in this course there's no final exam. There's a final project, individual one, there's a group assignment, and there's a quiz. You need to make sure that you are attending all these 3. Other than that, I'm fine. Okay, I don't care how bad you are doing it, but you have to do something. Okay, I don't want to fail anyone, so please try your best to at least do the bare minimum for me. Okay, even if you copy paste from somewhere else, it is fine. At least you write something for me if you think it is way too hard. Okay, then you can, if you feel it is safer for you to be in the class and take attendance yourself, you can just sit. If you don't want to listen, I won't force you. I won't specifically pick anyone to ask questions. So you are free to do anything you like. Okay, but try not to talk louder than me so that you don't disturb the others that want to listen. Okay, I can be very friendly with you all. You can make jokes around. It is totally fine. Okay, so I think that's all for the class rules. Then now, can I know roughly your names first? I will usually try to memorize student names. Okay, so for your information, I taught for 2 years in Asia Pacific University. I just came Xiamen last September. Okay, so the first semester I was very ambitious. I want to memorize everyone's name. And then the first semester I got instrumentation. So the class was like 96 students. So I couldn't memorize all of them, but at least I think I got 60% correct. Like in their final exam, when I walk around, I try to double check whether my memory and the face is actually correct. So around 60%. For this class also, I will try because I'm teaching 3 modules this semester. So I hope I will mess up your faces and your names. Okay. I probably asked a few times the first few classes, but just bear with it first. Is Jin Xuan here? Okay. I'm not taking attendance now. Later we'll try the attendance system because we have to try anyway. Is Yu Xiang here? I asked just now, no, right? Okay. Asan Ali? You are from? Oh, okay. Liang Yu? Ji Fan? Chang Jian? Wen Tong? Yu Hang? Chen Hao? I guess I should pronounce Peiwe. Okay. You're also Kazakhs? Komiko. Where are you from? Indonesia. So you are Chinese because you got a surname there. And then, so which one is your name? Which one is your given name? Komiko. Okay. Jia Kai. And there's one else here, right? Okay. So yeah, the rest are not here. So hopefully they are here the next semester. I mean the next class, because there are a lot of people dropping out the first few classes. So let's see. Now, so there's only 7 of you. Okay, so the 7 of you, I think you should be already in these teams. Okay, EE 315-2026/04. So the only communication channel that we'll be using is Teams. Okay, I like to use Teams because we can share anything we want. I can tag you all. I can share the files easily. And then one more thing is I will record the classes. Okay, so you can see that every time before the class starts, I will create a meeting and then I will join the meeting so that the classes are recorded. That's one of the reasons I say if you want to be physically here or physically not here, that you like to review after the class, it is okay. Because I say this class is hard, we might need a lot of revision review back the videos. So we need to probably record it down so that it will be better for you to revise back when you need it. Okay, so inside these teams, first make sure everyone is in these teams. If you are not, please let me know. So Teams is important over here because later I will let you know the notes are here. Okay, other things is inside Moodle, please check if you are in this Moodle. Advanced Analog Circuit Design 2026/04 Lian. Okay, if you are not in this Moodle, please let me know also. Okay, so if you're in this Moodle, you should be able to see final project question and marking scheme, group assignment question and marking scheme, class notes, and also group assignment grouping, which means that all the assessment other than quiz, I already set for you. I will brief you all today. Okay, I'll brief you all today, let you know what exactly that you need to do for your group assignment for your final project. So I have given you the first day. You should be able to submit at least the last day of this semester. Okay, you can start researching. Okay, okay, for class notes, when you click inside, there's a class introduction, and then there's chapter 1 for now. It's because there will be around 6 chapters along the way. But let's say I'll be teaching chapter 1 today, I'll upload the day before. Let's say I'll be teaching chapter 2 tomorrow, I'll be uploading it today. So you're following the pace, don't worry. We can for sure finish the class syllabus. I've taught this module a few times. So we can for sure finish up this syllabus by the end of the semester if you're following well. If you got any question, you feel free to ask me through Teams anytime. I will usually reply fast. Unless like I really miss your message. If you realize that after a few hours I didn't reply, please text me again, say hi. Okay? Please try not to email me because email will take a longer time for me to reply. Okay? What else? Okay, class notes. So class notes, the one in your PDF, the one in your Moodle is in PDF. Okay. Hi. May I know your names? And okay. So at least there are 9 of you now. Shall I start again? Okay, just a brief introduction, yeah. Like very brief. What is it here? Okay. So my name is Dr. Lian, okay, for your information. And then I have added you all into Teams. Where is my Teams now? Okay, into these Teams. Please make sure you are in. And then I've added you all into Moodle. Please make sure you are inside also. Okay, so these few things. And I just told them you can come anytime you want. Okay, for this class, I will always start at 11:10. Okay, I will always start 10 minutes late and end 10 minutes early. Okay, so like I said, you can do anything you want. You come just for attendance, you let me know also. And you can ask them, okay? So all the classes will be recorded. Later, inside Moodle also, there will be a link, class recordings. You can click inside and refer back to what I have taught today. So for those two that just came in, you can watch back the recording for what I have told them the first 10 minutes. And then, okay, so for notes, the PDF notes are inside Moodle. But if you want to access the real-time notes, okay, you go to your Teams. At the left-hand side, there's one thing called Class Notebook. You click on Class Notebook. It will load for some time. And then you can click on the bookshelf over here. Okay, and then under Content Library, here are the notes that we will be using that I can change on the spot, any updates over here. So if you want to see a better view, it is better for your tablets, for your laptop, to have OneNote app, or so that you can write directly on top, or your desktop to have OneNote app. So you can click on the top right-hand side, editing there, can open in desktop, and then you open something like that. Okay, that you can directly see, because the one that I put in PDF, I just print from here, and then I extract to PDF. Okay, and please bear with me as I use handwritten notes, because there are a lot of circuit drawings, there are a lot of formulas in this class. So it is better for me to just write it out on OneNote. But if you really don't like, please let me know. I can give you another copy. Okay. What else? Okay, so now we officially go to the introduction of the module. It's because it's my job to brief you all on this module, although you don't really need to know the details. But for your information, so this module, Advanced Analog Circuit Design, EE 315, and there are 3 CROs. You guys are year 3 now by right. From now onwards, you should know what is CRO, right? Course learning outcome. There are 3 CROs that link to PRO 1, 2, and 3. PRO 1, 2, and 3. Okay. CRO 1 link to PRO 1, CRO 2 link to PRO 2, CRO 3 link to PRO 3. So that's it, the part that I should brief you all. But here comes the part that what you guys really need to know. Okay. So basically these 3 PROs, it links to like fundamental circuit, data analysis, and then we need to link all our principle to what we call UNSDG. I'm not sure if you guys have heard of UNSDG, but it's the Sustainable Development Goals. Basically, like the whole world come together. There are a few countries that join together, and then they think that it is important to achieve 17 goals. There are 17 of these sustainable goals that they think that, oh, if I achieve this, then this world can be better. So they are trying to link all the applications, like everything that we learn, back to UNSDG so that we can contribute something. So whatever that you learn now, they might be like probably just helping to achieve, but you can always like explain it better to link back to UN SDG. This is for us to, this is a must because like EAC will evaluate us. So that's the only point. Okay. If you really think that it is not related, I mean, that's totally up to you, but you have to somehow explain it in your report. Okay. So this is the only part that you basically need to know for your syllabus. Total, you will have 3 assessments. 30% is your quiz. I would say the quiz will not be easy. I mean, there will be a lot of derivations. Okay. And then there'll be group assignment, 20%. You'll be grouped in 3 to 4 people. The submission is 3rd July, which is quite, I think, week 12 onwards. Okay. And then final project is individual. You must submit individual report, 50%. So this is the most important one. It will be at the last Friday of this semester. So generally, please make sure you at least submit, or you need to come to quiz. If you really don't know how to do, you can still get 70 marks, right? From the 2 assessments. And you guys know that the minimum mark to pass supposed to be 55. So these 2, as long as you submit something, I will try to pass you. Okay? Even if you just screenshot and then explain, I will try to pass you, but please, you have to at least submit. Don't let me text you and then chase you to submit something, because that's what happened last semester. So about group assignment and final project, I will brief you guys like 5 minutes later. So here's the structure. We will learn basically, you guys already learned analog electronics like BJTs, all those, right? So this is basically the BJT concept, but another version. So we know BJT is a current controlled current source, but this will be a voltage controlled current source. Okay, so it's very similar to what we have learned, but now we are doing it on a smaller size. Okay, I will explain later. And then there'll be amplifiers, single stage amplifier, differential amplifier, current mirror, frequency response, and feedback network. You can refer to all these textbooks or my handwritten notes, but I would say these textbooks, whenever you reading it will be a bit complicated. So whatever that I taught you now, it should be sufficient for your quiz and everything that you need to design. And you also need to download LTSpice, but we won't be using it so soon. But you can download LTSpice on your laptop, and then I will teach you how to use step by step and simulate your circuit. Any questions so far? Okay, all good. Then we will go to group assignment first. Okay, so this module, it is about analog. So you guys know the difference between analog and digital. So analog, basically, they are fluctuating a lot of times. Digital is only 1 and 0, so it's easier to design. So generally in our world, inside our laptop, inside our phones, there are amplifiers everywhere. For amplifiers, it is for sure is analog. And then there are oscillators. Oscillators as in the clock signal that we need is oscillator. There are rectifiers to rectify the charging AC to DC source that we need. And there are comparators everywhere. So that when it reaches one threshold, it turns to one thing. When it reaches the other threshold, it turns to one thing. So we think that these systems, probably the one that we learn, we design diode. We use diode to design rectifiers. And I think in BJT, do you guys design operation amplifier? So you guys also design operation amplifier. So similar things. In this case, we also need to design something like that is analog. But in basic level, we know that all these components, not just formed by diode, they are formed by transistor. So they are formed by transistor. It is very important to know all these transistor characteristics. Okay, so we don't need to go through all this. But okay, so here are the important parts. You need to form in a group of 3 to 4 people. 3 to 4. You can select your own group members. It is totally fine. Do not go more than 4 because I expect a lot from your report. Okay. So the design specification. You guys know what is transistor length? I think in BJT don't have this thing. Okay. So basically, you guys know that the old computer, the old phone, they are very big size, right? So why are they become smaller and smaller? It's because of something called Moore's law. Okay. So they say that they said after every year, the device size supposed to be 2 times smaller. That's why from a very big computer that can occupy the whole room, now become a laptop like this that we can use. So device getting smaller and smaller. When they are getting smaller, we say that this smaller size, the change is actually the transistor length. Transistor length. Okay. Have you guys heard of chip? So not the potato chips, but the chip inside our computers. So in this class, we are basically designing the chips inside our microelectronic devices. So those devices printing, there are a few big companies that do this type of fabrication. So one of it is, the biggest one is TSMC. It is in Taiwan. So TSMC is the biggest. I think it occupies around 70% of the production from the whole world. Okay. After that, they are everywhere. Even in Malaysia, there are a few. In East Malaysia, there's XFAB. In West Malaysia, there is Silterra, Global Foundry. So all these are from Malaysia, but you can see the ratio is like probably just 5% of the production from the whole world. So everyone is actually competing to see if they can build something smaller and smaller and smaller. So the sizing now, I think it can go sub-nano already. Okay, so the sizing that we'll be using now, which is the transistor length that we are using now, is 0.18 micrometer, or we call 180 nanometer. So imagine that after before this, you'll be using 350 nanometer, and that becomes 180 nanometer, and then 65 nanometer becomes smaller and smaller every year. But now it is already smaller than nanometer. But the one that we'll be using is 180 nanometer. It's because this is the easier one to design already. But just to get familiar, to tune the length, to tune the width and everything. So we're using this technology inside LTSpice. I will give you the library file that you can straight away see, what are the types of transistor there, what's the sizing that you can use and stuff. And then for this design, you can only use one supply voltage. So from top, we know that everything needs supply voltage. This is 1.8 volt. So imagine maybe our Arduino even, it needs 5 volt to operate. But this chip actually only needs 1.8 volt to operate. It's the minimum, it's the minimal voltage to operate already. If you give more than 3.3, it probably will break down. And I want your total power consumption to be lesser than 5 milliwatt. 5 milliwatt. Okay. And the load capacitance means the output that you need to connect is a 5 picofarad capacitor. So I have given you a few options here. There are 3 options in total. Each group, we only need to choose one. Let's say group 1 want to choose ring oscillator. Group 2 want to choose ring oscillator. You guys can do that. Everyone can choose the same circuit. That's no issue. But I have given you options. Maybe some people think that oscillator is easier to design, comparator is easier to design, rectifier is easier to design. So it's totally up to you. So let's say if you have chosen ring oscillator, you guys know what is a ring oscillator? Okay, so basically, if you can just search anyway, ring oscillator, you will see they are combining inverters. You guys know what is an inverter? Okay, inverter means it can invert your signal from 1 to 0, 0 to 1, right? So it is a ring of inverters that can go. So they connect inverter, 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 and then they link back to the first stage. So this is what I call a ring. And then this thing, once you connect like that, it will give you a square wave. So the first design is ring oscillator. Okay, there are a lot of topologies out there. for this course, I will only teach you the transistor basics, like the transistor basic, how do you build amplifier and stuff. Let's say oscillator, you already know the working of an transistor. You need to build that yourself to make it a string to have the oscillation. So you can always search anywhere online to find any paper, get one topology of that, you simulate the exact same thing, it is totally fine. Because this course is want you to explain how it works. Okay, I will teach you the basic of how it works, and then you need to use those basic to explain your circuit. So the target oscillation frequency, it needs to be in between 1 megahertz to 20 megahertz. So you can swing up to 20 megahertz, or you choose like 10 megahertz also can, but it must be in this range. So in the end, it needs to be a 5-stage. Link back the output, you will connect to one 5 picofarad capacitor, and then you can see the swing. The swing is around 0 to 1.8 volts because your VDD is 1.8 volt. Or the second design is a comparator. Comparator is also very common in your designs, in your analog circuits, okay? Because these are the basic things that inside our analog devices. So comparator, you need to build a 2-stage comparator. What's the use of comparator? You will compare with one source. So let's say you want to compare against 0.9 volt. You can only use one DC source, which is 1.8, right? And then you will voltage divide it probably to 0.9 volt. That can be your reference voltage source. And then I want you to compare that reference voltage source with any input voltage that you want to put. So your comparator needs to be a 2-stage comparator. You can use any design again. And then the input will be a 100 milliwatt peak-to-peak voltage versus any voltage difference, voltage reference, which is maybe 0.9. So you can tune, you want 0.9 or you want 0.1, 0.2 against this 100 milliwatts. So you tune and compare. So basically what comparator do is, if you are given, let's say it will have left to right. Left is your reference, right is your input. If maybe left is higher than right, it will give you a high voltage of 1.8. If the other side is higher, then it will give you a voltage of 0, near 0. So I want to see this effect over there. Okay, it can even able to detect a voltage difference of negative, lower than 20 millivolt. Let's say this is 100 millivolt, this is 120 millivolt. It can also detect the difference. The third option is rectifier. You guys know what's a rectifier, right? It rectifies the AC voltage to DC voltage, to DC voltage. So it needs to be a MOSFET base, which is the CMOS that we'll be learning. You can use any topology again. Usually it's a cross-coupled design is the best. You can just search CMOS rectifier and see if that is the easy one. So input needs to be a sine wave of 300 millivolts. And then your output needs to be a stable output. You can stack different stages of rectifier to pump it up also can. And then the ripple needs to be very low and connect to the 5 picofarad load in the end. So from these three, you will choose any of it and design. So as mentioned, there's only one DC supply is allowed. Only one DC supply is allowed. Okay, other than the comparator design. Comparator design, you need to compare with one DC source, right? So the one you can use a separate DC source is okay. You need no need to voltage divide, also fine. You need to compare that with your input value. So that two input value and the reference voltage, you can use two different ideal sources. That is okay. Only for comparator. Okay. And then you cannot use other biasing. You can only use current mirror to bias. You all learn current mirror in BJT. So you can basically mirror one current to other places to use. So you need to use that as a biasing. For ideal resistor and capacitor, you can only use one resistor and one capacitor. The other one is your capacitor load. So here are the design constraints. So you work as a group to divide your work yourself. Usually I will give everyone the same marks. unless like two of you, like let's say 3 of you in a group, 2 of you texted me, say that the other guy really didn't do any work. You show me the proof, and then I will deduct the marks from that guy only. And then you will need to basically show the most important point. You don't care whatever I wrote here, but the most important point is you must be able to show or explain how this circuit works. Like run the DC analysis, whether this transistor is turned on, and run AC analysis to show me the sine wave. So the submission is 3rd July. No turn-in is required. That's why I say you can just take any circuit anywhere, but you just need to explain. You don't need to submit turn-in for this group assignment. The group will submit as one PDF report. So only one person needs to submit per group. So you make sure everyone's name is inside. Any questions so far? There will be a lot of questions now, like you don't know how to design, but we will learn along the way. Or if you got any circuit already, you come to me, I can roughly explain to you. Okay. So the components breakdown. Here are all the marks for this group assignment. Okay. So the first part is, for sure, you need to have the cover page with everyone's name. And then you need to tell me which circuit that you have selected. The ring oscillator, the rectifier, or the comparator. There's no specific layout for your cover page. You can use any cover page you like. The second one is your circuit topology and theory. So basically, you already did. Let's say you are copying from somewhere. You don't just screenshot, you draw it yourself. Okay, you can use Draw.io or anything visual also can, that you draw your circuit out, or you just screenshot your schematic from FGSpice also can, and then you need to explain it. So the most important part is detailed explanation on how the circuit operates. Like, why do you need this transistor to be here? This is the differential pair, or this is second stage is for what, and so on. And then you need to say that, oh, this should be in saturation region, something like that. The regions you will learn like supposed to be today. The second part is the mathematical modeling and circuit explanation. So let's say for ring oscillator, you will find any mathematical equation that related to your circuit. Let's say rectifier. In the end, you will need a V out. So you will say basically if it's a full wave rectifier, you're supposed to have these two waves add up as your V out. Or for oscillator, how do you calculate the frequency? For comparator, whether it will follow your VDD or your 0 volt, something like that. So you have to put in the fundamental equations related, and then mathematically explain, especially your biasing circuit. Like your current mirror gives how many current to the other side, and so on. The other part is the tuning process. So basically, you are tuning your circuit. Initially, for sure, you can't get the result that you want. And then you will tune the size of your circuit. Let's say just now I mentioned the length of your circuit. But instead of length, there's also width. You will control the width. You change from maybe 1 micro to 2 micro to 3 micro. And then you check the difference until you're able to get the result that you want. And then you record down everything. So you say initially it was like a very dead circuit. And then you increase the width sizing already, it becomes better. And then you increase the resistor, it becomes better. I want you to show the whole tuning process. And then you need to check whether the power is lesser than 5 milliwatt. And then after that, you show all your results. Okay, you just screenshot your results, DC analysis result, transient, AC analysis if there's any, and then verify power. You put the graph and then you explain. So this is the result of what thing, or what is showing here, something like that. Then number 6 is the easiest one to get marks. Basically, you just need to link back to 2 UN SDG. Choose any 2 sustainable development goals to discuss about it. And then you say that you need to say how analog design actually influences the whole world. How do we reduce carbon footprint and stuff? So these are basically just for you to, these are non-theoretical. Okay. for you to say anything that you liked, as long as it looks okay. You create your own story for this. So you see, if you don't have any design, you already got 15 marks because you just need to create the story. And then discussion and conclusion, you discuss what's the weaknesses. You discuss whether, in summary, you have met everything. Okay, if you cannot meet, it is totally okay. You explain why. So here are the marking rubrics. And then in the end, please attach your marking rubrics at the end of your report. Okay, I will just mark from there. Any questions so far? Okay, you can start working on it because it will really take some time. But this part, I already reduced the analysis. The last semester, the analysis is slightly more than that. Okay, so that's why I say there's no Turnitin. You can use any AI tool that you want, but at least you need to make sure you know what you are doing. You know what you are doing, that's the main point. Okay, you can use AI, but it might give you a lot of wording you just copy paste inside. I can sense that, but I want you to understand your circuit. If you really don't know, AI already explained to you, you still don't know, you can come to me. Okay, there are a lot of semiconductor interviews that will ask these fundamental questions from this module. So once you have decided your grouping, you can click on group assignment grouping, this link. It will go to a Google form. So fill up this Google form. Fill up this Google form on who is the leader, and then the group member's name. Okay, sorry about that. Okay, so just fill up. You can fill up anytime you want. Just before the submission, it is fine. Okay. So are you guys still with me or already feel it is too hard to do? Still okay? I think BJT is slightly harder for me. BJT is slightly harder. Okay, so if it is okay, let's continue with final project. Okay, so you have known all the assessment in today's class itself, the first class itself. So you can already expect what happens the next. Okay, so I'll let you know first. So for this project also, you will need to design a circuit. You also need to design a circuit in LTSpice. Okay, basically for analog design, you don't need to see the introduction. You just hear my explanation is good enough. So basically for analog design, we also design sensors. Okay, I believe you guys know sensors, temperature sensor, LDR sensors, all those. So these sensors, they basically convert, they have some chemical thing inside that can convert one form to electrical signal. So let's say your force sensor, when you force very hard on it, it probably just give you a slightly change of maybe 100 ohm. And then you press harder and harder and harder, you probably just get a little bit of it. So the change is too little. So you want to amplify this change, you have to use amplifier. The amplifier that we use will be, we call OTA, which is operational transconductance amplifier, which is the operational amplifier that you do, similar in BJT. So in this one also, you have two options, okay? Just, I give full flexibility for you all to choose which one that you think it is easier. You choose only one from these two options. The first one is a temperature sensor monitoring circuit. So you imagine now, you get one sensor already, temperature sensor already. You want to amplify this signal condition it so that you can get something in the end, whether it is high or low. So you will need this. So basically, you want to design that the system will amplify the signal from temperature sensor, and then you will need one comparator after this. Remember, you already built comparator probably in your group assignment. You need a comparator to convert the amplified signal into one digital output, either 1 or 0, or high or low, when it exceeds certain threshold. So here are the parameters. Again, you will be using 180 nanometer technology. And supply voltage will again be 1.8 because 180 nanometer, the supply voltage optimum is 1.8 volts. The sensor input, you will expect you are getting a 5 milliwatt input or 20 milliwatt input. Okay, that's the temperature sensor input. And then I expect you to have the transconductance, your operation amplifier gain, to be more than 30 dB. Okay, we'll learn how to calculate the gain later. How do we determine the gain later? But it means the AC gain needs to be more than 30 dB. And then the bandwidth of the circuit, it needs to work for 15 kilohertz. I will also teach you how to check the bandwidth of the circuit. And then the comparator threshold. So let's say you need another separate voltage source for comparator. The ideal threshold voltage source, it is 0.3 volt. You will compare with your amplifier, and then you will give the output. Okay, so let's say your input is 20 milliwatt. You need to amplify maybe up to 0.4. Amplify until it is 0.4, and then you compare 0.4 with 0.3, or you will compare 0.2 with 0.3. So it's totally up to you how you design it, how you explain it. That's why I say, as long as you submit, I can give some marks because it is totally free. The whole design is very flexible. And then you need to drive an output load of 20 picofarads. And the power consumption, total power consumption needs to be lesser than 10 milliwatts. So this is the first design, first option. The second option, it is a vibration sensor signal conditioning. There are some vibration sensor in our car so that you determine whether there's any mechanical fault inside your car. So this system will tend to amplify the vibration sensor signal. So we know vibration, it keeps on going up and down, up and down. There are a lot of oscillations. So instead of just amplifying it, we amplify the signal first, and then we want to filter out the unwanted signal. So we need a filter. Filter, it can be RC filter, just a simple resistor capacitor network, that is okay. Or any high pass filter that you can design, also can. So the same thing applies, but I want your cutoff frequency to 1 kilohertz. That's the only difference. So you can only use one DC supply again, except for the one that with comparator, you can use 0.3 volt DC supply, and then one input signal source. Maximum only one resistor, 2 capacitor, including the load. Again, the same thing. You must use biasing circuit. You must design the operation amplifier. You must use biasing circuit current mirror. You cannot use ideal current source. The deadline is 10 July. And this one you need to submit, turn it in. Although I write lesser than 25% is required, this circuit basically, it is very hard for you to turn it in unless you really copy paste everything inside. You cannot copy paste from somewhere because these circuits are not available. I mean, there's no specific circuit for temperature sensor, for vibration sensor report. Okay, there are circuits like OTA, there are circuits like RC network. You can copy that, you can but you explain in your own words, supposed to be okay. I don't check AI similarity. Okay, that's the good part. I don't check AI similarity. Basically, you can use AI. But again, to be true to yourself, you need to at least know what the AI is teaching you. You just copy paste and put inside. So here are the marks division. You have your cover page. You choose, you tell me which one is your circuit option. And then architecture description. So introduction, you explain what is the selected sensor application. Explain what is temperature sensor, what you do and all that. The system architecture, say you explain, say that, oh, you will have OTA, you will have filter, you will have RC network, you will have comparator and so on. And then you will say you expect the flow, like let's say input signal is 20 millivolt, you go to your OTA, it amplifies to 0.5 volt, and then you compare with a 0.3 volt, what is your expected output? Next one is the design and analysis. So we design the OTA. So the most important part for this assignment is the transconductance amplifier. So you design the amplifier and then you explain everything in very detailed, including like what is the working principle of it, how does it amplify, and then any relevant equations that we learn for differential amplifier you can put inside. Small signal model of that amplifier. We learn how to draw small signal model for MOS circuit, how you calculate and all that. And then the biasing network, the current mirror also you need to explain. Then the secondary circuit. Secondary circuit, let's say for your temperature option, secondary circuit will be your comparator. For your vibration sensor option, secondary circuit will be your RC network or any filter that you put. So you need to explain how you design that. What is the cutoff frequency or what is the voltage, how it works, what is the bandwidth, whichever relevant formula you just put inside. So I didn't specify like you must put this, you must put that. You just put whichever that you think it is relevant. And then you need to present all the simulation results like DC point, transient, frequency response, output. And then you explain the graph. And then discussion. Okay, for discussion, this one is not just about UNSTG. You need to mention to me what is your result. Like what is your gain in summary? What is the bandwidth? What is the power consumption in summary? And then you need to link to UNSTG. Okay. And then here is the marking rubrics. So again, you need to attach this at the end of your report. After you write everything. So these are the only sections that will have marks. So basically, you don't need any other section that don't have marks. Okay. So you keep your marking rubrics in the end. After marking rubrics, you attach your Turnitin, only that result page, only that page. Combine as one PDF and submit. Any questions so far? Okay, if no, let's have a 5 minutes break and then we start chapter 1. Anyone already feel it is too hard up to now?随便问一下 if you guys don't mind 啦 OK 有谁现在是 first class 的 like 就是3.7 and above 的 CGPA yeah 没有就是我I mean 很多人会 expect what do you guys expect in this class 会很想要看你想要学什么，或者你真的是一定要拿 A+ 的，一定要拿 A 的，或者你们来纯粹就是为了要 pass 的？有人来为了要 pass 罢了吗？OK。
Stone 是一组的，就是我是王悦的组员。
OK。
我然后问你一下，你喜欢什么样的那种开会形式？
我其实都 OK，就是看你们喜欢怎样的都是。你们要 online，你们要你在我的办公室，
就是可以去你的办公室线下开会吗？
可以可以。你们可是王玉还没回来的。
啊，对，他这周六周日应该会。
OK，这样下星期二我会不在，星期一我会不在，星期三暂时都还行，我们就叫他 text 我，然后我们安排一个时间，就是暂时星期三、星期四、星期五都还行。
那3天都可以。
对，最好就是星期五这个课之前的，因为我10点到11点，就是我上个到10点，然后我11点再上你们的课，所以10点到11点一定是在空的。
下午你就休息了嘛？
没有，
周
因为通常我们拜五下午会有开会啊，拜四的话就整个中午都行，拜三整个中午都行。
礼拜三、礼拜四的中午，
嗯。
那我们需要每周把成果什么的给你汇报什么进度。
我觉得 Capstone One 不需要，Capstone Two 可能我才需要。Capstone One 你们去做了过后交 report，大概是这样的形式。
Stone Two 就是 FYP
不是 Capstone Two，因为你们这个 project 是需要做2个 semester 的，
啊，
然后你们的 Capstone Two 的时候呢，你们就需要建一个 prototype 出来的，就需要做一个东西出来。Capstone One 只是写 report 了。
大四上学期做开做。
对对。
那我们这个 Capstone 是今天下午不用上，是下周才。
我不懂你们有没有上课，因为我们是你们的指导老师，可是我们不是那个给你们 briefing 的，就是你们会有一个老师给你们 briefing，跟你们说你们是需要交什么 report 形式是怎么样，是另外一个老师跟所有人讲。我们只是指导你们做你们要做的东西，就是你们的 project 的 technical part 是我们指导。
谢谢老师。
Okay, you guys ready for the first chapter? We only touched the easier part this today, so don't worry. Okay, so first of all, what we are learning, we will be using this device the whole time, is what we call MOSFET. MOSFET, okay? So you can see the first word of this MOSFET, MOSFET, which is what we call a metal oxide silicon field effect transistor, okay? Or some people also call them MOS device, metal oxide semiconductor device, or some people call them CMOS. CMOS stand for complementary metal oxide semiconductor. So they are the same thing. Basically, from the name itself, you can already think that, oh, so this device has metal layer, has oxide layer, and also silicon layer. They have these three layers and then form as one transistor. So for this transistor, there are two types. One is what we call the NMOS. One is what we call the PMOS. It's like your PN junction. So how does PN junction form? It's because it's normal silicon that have 4 valence electron outside, right? So they are not conductive yet. When they have formed a silicon bond, basically they're covalent bond together, 4 plus 4 together, so it's 8. They cannot move. So for N-type material, PN junction, not just this one, for PN junction, they will adopt something that is more negative. Let's say a boron. They will have, let's say, 5 valence electron. They will drop inside, and then this will be the extra electron. So that's why it is called N-type material. For P-type material, they will find something with 3 valence electron that dope inside, and then now you will have 1 less electron, which means it will have 1 extra hole. So this is what we call the P-type material. So over here, we basically have the N-type and P-type material formed together to form one MOS transistor. So the diagram that I draw over here is what we call NMOS transistor. NMOS transistor. You ignore the green color part. We only see the black color part now. So basically, a transistor is very, very small. I enlarged it already. The 3D diagram, it looks something like this, which you will have one gate on top. This gate is we call it metal oxide semiconductor. So gate is the metal. This is the part that we usually connect something on top. Then we can conduct electricity because it's a metal layer. But just right underneath the metal, you have this part. It's what we call the oxide. It's a 3D diagram here. So it's what we call the oxide. So we got metal oxide already. We got 2 layers already. So is oxide able to conduct electricity? No. Okay. Oxide cannot conduct electricity. So this is just a layer over there. And then at the bottom, it is basically like a bed. Okay, this bed has what we call the P substrate. P substrate, which means it is heavily doped with P-type material. So there are a lot of holes there. Okay, P-type material over here, the whole thing. And then they will dig 2 holes. They will dig 2 holes at the P-type material. These 2 holes, they will pump in N-type material, which what we call N+. So they are very negatively charged. The N+, N+. Okay, so this N-type material is somewhere in between the gate. So you can see half of the N-type material is connected to the gate. The other half is just outside. Half of the N-type material connected to the gate. The other is just half outside. But not just that. We do not have 3 terminals only. Okay, so we do not have just all this. We have also something called the bulk, or what we call the body. Bulk or body. This is also P plus material. It's basically this P substrate is P, right? So it's over here. We say this is the bulk. Okay, because we also want to connect something to the body, to this substrate. So we put it up there. We call it the body. Okay, so for resistor, there are 2 terminals, right? In and out. For capacitor, also in and out, 2 terminals. For BJT, how many terminals that you have? For BJT, there are 3 terminals. Okay, the emitter, collector, and what's the other one? Huh? Base, yeah, the base. Okay, so we have these 3. So over here, we not just have 3 terminals, we have 4 terminals. Okay, the first terminal is the gate. So we can connect the gate. Gate is the base. Okay, and then we will have 2 more terminals. They are connected at the end part of this. The end part of this. Okay, so right after this, they'll go up. This is the drain. This is the source, or interchangeable. And then this is the bulk. Okay, so total we have 4 terminal. So if we draw it in a simpler way, you can see it like this. We have the gate, we have the source, we have the drain, and then the body. Sometimes people will show, sometimes people will not show. Okay, I will tell you the function of the body afterwards. But if you draw as a symbol inside your schematic, it looks something like this. The gate, and then you see we leave a space over here because this is the oxide. The source and the drain. Okay, so for NMOS devices, we say it is going out. The arrow will go out. For PMOS devices, the arrow will go in. So there are a few ways to draw NMOS and PMOS devices. So there are different types, different symbol. They're also meant NMOS, they're also meant PMOS. Okay, so this is NMOS. This is NMOS device because the arrow go out. Or okay, I'm using mouse, so a bit hard. This is PMOS device because this arrow go inside to the oxide. Inside is PMOS, outside is NMOS. Okay, or sometimes they don't have the arrow. So if you copy the circuit from somewhere and you don't understand, sometimes they don't have the arrow. Like this is NMOS. But for PMOS, they have a circle on top. It's like your inverter, something like that. So you will have a straight line, a circle, like this, and then only draw downwards. This is your PMOS. With a circle is your PMOS. Okay, so generally you might have this kind of symbols. So the good thing about MOS device compared to BJT is that you will realize because collector emitter, they cannot switch their places. But for for MOS devices, we can switch places. You can see I label this S, I label this as D, but it looks like both places are the same. So we say that they are basically symmetrical. I can put my D over here, I put my S over here, that's totally fine. So it means these devices, they are good and bad. These devices, they are bidirectional. For BJT, current can only flow one way, but for this one, current can flow both ways. Or we say that the voltage can flow both ways. So let's look at the first condition. The first condition, you look at this diagram only. Okay, so I only give a voltage to my gate. A very small voltage to my gate. While now my drain and source, I ground them. My drain and source don't have anything, but I put my gate. Okay, let's say my gate now is very, very low, 0.0001 volt. Okay, so basically like nothing. So what happens is it will have this blue color circles, the negative ions over here. Okay, so you imagine right now, still remember what is this bottom bed? This bed is a P substrate, right? And then you have this N on top. So it looks exactly like PN junction, right? We got N, we got P. So it looks like PN junction. So when PN junction put together, even without any voltage source, we say it will form a depletion region already, right? Because they will go by diffusion. Because of diffusion, they will already form a region. So this is the depletion region right now. Okay, got negative ions, means is current conducting? Current is not conducting because negative ions, they are kind of fixed over there. They are not moving. Only electrons can move here and there. So this negative ion, basically this circuit is now not working. Okay, so if that's the case, we try to increase a little bit. We try to increase our gate voltage so that it becomes more than the threshold voltage. You guys should know what's the threshold voltage already. So the minimum voltage for this device to turn on. Okay, so let's say now I increase slightly until it reaches the threshold voltage. My gate voltage, we call it VG, is now the same as your threshold voltage or more than that. So what happens? So now instead of, so this region now is so much positive than whatever over here. It will attract all the electrons up. Okay, the moving electrons, it can attract up. So now electrons are the orange color part. It will form the orange color part, not the negative ions already, because it got more positive energy to attract all the electrons up already. So this part of it, the brown color, the orange color part of it, we call it a channel. A channel. So what exactly is a channel? Channel is just a pathway. It's like a route. I put a route for you. It's a pathway prepared for your current to flow. Now, current is not flowing, although electrons go up already. But it's like a BJT. Current is flowing horizontally, like emitter collector. Okay, so basically now we got the current, we got all the electrons, but it is not moving. We just go up already on the, okay? So right now we can say that as your gate voltage increases, the electrons move up, and then there's a resistance between drain and source. So electrons move up, but then right now both are 0 volt. Drain and source are 0 volt. Okay, so this device we will say is basically turned on because of the gate voltage already exceeded the threshold, but there's no current flowing. So far, any question? Okay, I will assume there's no. Second condition now, let's say I already given enough threshold voltage. I maintain that my VG is exceeding my threshold voltage, so device is turned on, but no current flowing. So now I try to put my source to ground. So my VS is the voltage source, the source voltage. My VD over here is the drain voltage. Okay, my VD over here, I say I connect a battery. I connect a battery. So what happens? So you will realize that here there is voltage already, right? So whenever this is more positive than source, current goes to the left-hand side, right? Current will flow from positive to negative, right? Okay, so current flows this way. Okay, so basically it's because here is more positive. They will attract, remember just now there are the orange electrons that are not moving. So this is the positive part. It will attract the negative ions, it will attract the electrons to right-hand side. So whenever electrons go right-hand side, your current goes left-hand side. So we have a current flowing to the source, from drain to source. This is what we call the drain current. ID is what we call the drain current. So you can see if we draw ID versus VG, if the gate voltage is very low, lower than threshold, we got no drain current at all. And then after that, we think that if we keep on increasing VG somehow, I know just now we put VG, the electrons go out on it. But if the movement is too large, the VG is so big, for sure it will cause the electrons to move a little bit. So we say that it might behave this characteristic, but it depends on your drain voltage later on. Okay. So you imagine now, the drain voltage getting higher and higher, what will happen? So imagine now the VG is already more than VTH. So we try to plot ID versus VD. ID versus VD. Drain current versus drain voltage. So as the drain voltage increases, I push more electrons to the other side. So my current will supposedly increase linearly. So when it increases linearly, so you can see your transistor actually as a resistor. You can see it behaves actually more like a resistor now. Okay. So when VD increases, ID increases. So far, any question? You guys still following? Understand? 很犹豫, okay? Very, you guys look a bit confusing, but I hope still okay until now. Okay, so just to conclude, okay, because this is just a revision of what I have, we have on the structure. Okay, I will just write on board, but then we can go through that. I mean, is the notes on the board already? The notes on the OneNote already. But basically, we say that the first case. Okay, so you first need to remember this is gate. VG is gate. Second is VS is source. Third is this is drain. For your device, you must draw. So at least if it is not 3D, you have to draw a 2D diagram. This is your gate. This is your drain. This is your source. So this is the diagram that you at least need to draw. So you imagine at the first case A, we say that VG is very low than threshold voltage. So VG is very low. Basically, this is just a PN junction because here is P, here is N. So that will basically create depletion region. When we say depletion region, it means that there are negative ions here. Okay, so these negative ions, what happened? They are blocking because it's a depletion region. So my device, I cannot see anything to my electrons yet. Okay, then after that, I try to change a bit. I change my voltage source. I increase a little bit. So now here, the voltage increases. VG increases a lot. So what happens? We know that deep down, there are electrons somewhere. So deep down, there are electrons somewhere. Now the VG is so high. So it's more like a capacitor. You can see there are metal. Inside there's a dielectric. So it's like a capacitor. So MOSFET can act as capacitor. But right now, I think it can act as resistor also. It's because, okay, so VG increases. I can absorb all these small electrons to up there. Okay, so we can see that this basically they break this depletion region already. And these electrons, it moves up. This electron is moving up. So now it will become a region. Okay, so we might need to see this diagram a lot of time, at least until now. So this is your gate. Okay, so now we will form electrons here, but are they moving? Seems like not, but we think we can move them later. So we connect drain voltage. Okay, so we connect drain voltage to check whether we are able to move them. Okay, so just to let you know, although they are bidirectional, we say that they can move two ways. But usually we try to, for NMOS, we try to let the current flow from drain to source. For PMOS, it is the total opposite. When we say VSD, when we say ID, S, drain to source current in NMOS, so we will say this is IDS for NMOS. But for PMOS, we will say it is always flowing from source to drain. We call it ISD. Everything in PMOS is totally inverted as PMOS. You just need to remember that. Everything in PMOS, inverted. So from here, the drawing is still the same, if PMOS, but you need to change this N to P, change this P substrate to N. That's it. Okay. Then next case, I think that I want to increase. Case B, sorry. Vg is more than Vth already. So this is case B already. I already got the ions here. Case C, now I add a Vd. So we say VDS because this source will connect to ground. Now I put a voltage source over here. So whenever ions is here and you put a voltage source, what happens? It will attract the ion to the left hand side, to the right hand side. It attracts all this free ion to the right hand side. So your current is actually flowing from drain to source. Your current is flowing the opposite direction as your electron direction. So your current now flowing from drain to source. And we say that the more it pulls, the higher the current it flows. So the higher the Vd, the higher the ID. So this is the only things that you need to know for now. Next is the IV characteristic. IV characteristic as in the current voltage characteristic of this device. So we say this device over here, imagine that Vg already more than 1 volt. So already more than 1 volt, which is more than the Vth. So we keep this on. Device is on. Now, my source, this is connected to ground. My drain is connected to Vd, which is 0.5 volt, let's say. So what exactly happening? You see these two N, they are connected somewhere to the gate also, right? Due to this connection, they are connected just right below the gate. So what is their voltage difference now? Let's examine. We say that Vg is 1 volt, Vd is 0.5. So 1 minus 0.5, we got 0.5 volt voltage over here. 1 minus 0.5, the drain voltage over here is 0.5. And then 1 volt minus the 0 volt over here, the ground. So here basically, because here is 0 volt, here is 0.5. So basically we have a voltage difference of 1 volt. 1 minus 0, we got a voltage difference of 1 volt. 1 minus 0.5, we got a voltage difference of 0.5 volt. Okay, we see only at voltage difference now. So we say that the voltage across this channel, in between them is what we call channel, yeah? So this channel voltage increases from source to drain. You see, the voltage difference here is 1 volt at source, but the voltage difference here is 0.5 volt. So we say that the voltage difference is bigger at the source compared to drain. So we say voltage across the channel that increase from source to drain. Agreeable? Okay. Then, since the change of voltage increase from source to drain, we say that the Q, okay? The charge is basically proportional to your voltage, right? The larger the voltage, the more charge density that we have. So we can say that it actually behaves this. So imagine here is your source, here is your drain. Because the voltage is lesser, voltage difference is lesser. So I suppose here we have lower density charges. Here we have higher density charges. Agreeable? Because here I got 1 volt compared to 0. Here I got 1 volt compared to 0.5. I only got 0.5 volt. Okay, so they behave as this characteristic. So far, okay? Right, next. So now is the formula, okay? Because when we say we want to derive IV characteristic, basically our final aim is just to derive ID, the drain current formula, okay? So initially we say charge is equals to capacitance times voltage, capacitance times voltage. And then what is the capacitance over here? We say that this whole device looks like a capacitor because we got one metal, the other metal inside is, in the middle is dielectric. So we know capacitor is always about how big the surface is. The bigger the surface, the larger the capacitance. So we can say the capacitance is just Cox, which is the capacitance of the oxide per unit area, times with the width of the device and the length of the device. Okay, I haven't tell you, but this is the length. The distance between the drain and source is the length. How depth it is, that is the width. Okay, so we can say that capacitance, or the charge total, is the whole width length times the total capacitance. And then what about the V? What's the voltage? Because we know Q equals to WL Cox. This is the capacitance already. But what is the V? The V is the driving voltage. So let's say our drain is 0 now. Our capacitor, before we connect to anything, also it already got a capacitance, right? So this capacitance is due to, it is already turned on. It's due to, there's already a voltage at the gate. Okay, the gate is already over the threshold voltage. Then only we consider this as a working device. So we say that the voltage over here must be Vg minus Vth at least. Vg minus Vth is what we also call overdrive voltage. Okay, remember this equation is we assume the total charge of the MOS device when your drain voltage is still 0. So we got this formula. This is the total charge of the device. But what if I want the total charge density? Like I only want to see one part of it, one part of it, one part of it. I don't want to see as a whole device. So I can divide by the length. Okay, I don't care. I just want to see one part of it. Okay, I just want to see a small part over here. I cut a small part, I see in terms of the whole width, but a small length of it, a small length of it. So I divide by length. So it was WL Cox. So I remove the length already. It becomes W Cox Vg minus Vth. This is the charge density per unit length only. Okay, so we only care about per unit length now. So we ignore the rest. So what if your Vd is not 0 now? Let's say Vd now got the 0.5. So you can see this is the length, right? This is the length that I mentioned just now. So here is, let's say length equals to 0. This is length equals to the full VDD. So what will be the length if my VD is not 0? You can imagine here is 0, here is 0.5. The voltage actually dropping along the way, right? 0.5, 0.4, 0.3, 0.2, 0.1, and then go to 0. The voltage is getting lesser from right to left, the drain voltage. So we can call this as our x-axis. Okay, so we can say that depending on the different length, we call them Vx. So let's say I want to find the voltage, the charge density at the middle point. My Vx will be 0.5 or 0.25. I want to find the charge density at this point. So my Vx will be 0.5. If I want to find the charge density at this point, my Vx will be 0, and so on. Only at each different length. But right now, we only found the charge. We haven't got any detail yet. So what exactly is a current? Current means how much charge is passing through. I sit here, I see the charges passing through in 1 second. That's my current, right? So how fast the current goes in 1 second? So that one is velocity. So current basically is your charge times velocity. Okay, and then velocity is equals to mu E. Okay, we call it mu E. Mu is the mobility of the charge carrier, like how mobile my charge can move, how mobile my electrons can move. E is the electric density. Electric field. It's the electric field. E is the electric field. Okay, like what's the voltage difference that can attract these things go up? So that is the V. And at the same time, so this is the first formula. And second formula, we already know the basic formulas. Then electric field, what does it mean? It is negative, the change of voltage per section. So we can say it is negative dV over dx. These three formulas are the very standard formula that you should learn already in electronics 1 or 2. Okay, you just use back. So right now, I want to find what is your velocity. If I want to find what is my velocity, I can substitute. Velocity is my mu times E. My E is negative dV dx. So now my velocity is negative mu dV dx. Negative mu dV dx. Until this point, is that okay? Still acceptable? Still logical? Okay. Next. Remember, our aim is always to find ID. Our aim is just to find ID. Okay, so let's say I want to find what is my current. So see over here, my current is basically Q times velocity. Okay, you ignore the negative part first, yeah? You don't see that I added negative, but ignore that first. So I say Q times velocity. I already have my Q just now. Charge density Q just now, up there. So I move this, I say Q is my Q density times with velocity. And then I derive this one, the Q, which is WCox Vg minus Vth minus Vx. So I just substitute inside. I do substitution only until now, times my velocity. I say this is my ID. Okay? But exactly what is my ID? My ID, I don't want to have velocity because I can't be measuring the velocity all the time. So I want to see in terms of its mobility, the voltage difference. So I need to substitute this one somehow. Okay, I need to substitute this equation somehow. So in the end, okay, so I would say that, okay, another term. Why do we need negative over here? Okay, so normal formula is just VQ. But remember now, these are the electrons' movement. But if we derive in terms of current, electrons are moving in different direction, right? Current is the opposition of your electrons in different direction. So we have to add one negative so that they are opposing the direction. Okay, because our charge just now, we assume it is positive. Now, they are moving in different directions, so we add a negative in front. So our formula got negative already. So you see, this is our formula so far. Now, I want to change this velocity into the thing that we derived just now, the negative u dV dx. So if I put negative times, replace with this velocity, negative, negative become positive. This v becomes un, mu and dV dx. And then WCox Vgs minus Vth Vx. These are still exactly the same thing. But mu n dV dx, I moved down already to replace the velocity. And it becomes positive. Okay, so you will see now I'm writing in terms of mu n, because the mobility is very different. Okay, remember there are P and N devices. So we got PMOS, we got NMOS. So for NMOS, the majority is electron. For PMOS, the majority is the holes. So right now, for electrons, we will say mu n. Mu n means the mobility of the electrons. Mu p means the mobility of the holes. Okay, since we are discussing NMOS only now, we put mu n, dV dx, WCox something. So we say this is this formula now is our current. Oops. Is it agreeable that this is our current? So far, the derivation is still okay. Okay, so usually when you see current, you want to see in terms of one values, right? Do you still want to see dV dx, all those? All right, we don't want to see the dV dx. Okay, so this dV dx over here, this derivation seems to be very annoying. We want to remove that. So we move the dx to the left-hand side. dV we move to the back. Okay, so we go until here. Basically, it's still the same thing. Our WCox is over here. Mu n is over here. dV we move already. dx we move to left-hand side. Vgs, Vth, Vx is still the same thing. But right now, we are not just looking at one side now. You want to look at the whole thing, the whole length. Okay, so if the whole length, how do we do? Is remember ID. You know what is the use of integration? So integration, basically you want to know everything about every point. So now you want to add every point together. What is the current at every point? So we use integration. We will integrate. We want to find what is the current for the whole length, effective length for the whole length. So we say it's the length from 0 to L, to your drain, basically. So if it is from 0 to L, then at the same time, it will be your voltage from 0 to your VDS, which is your VD, because your VS is 0. Okay. So we integrate something like this. So after integration, this will be your L ID. And then W, mu N Cox W. And then over here, we will use, you will integrate, and then you will get VGS minus VTH times V minus half V squared from 0 to VDS. Okay, so this is just a normal integration. Okay, so V is now the term that can change. Okay, so after this, you will move this L, because my aim is to find ID. I don't want ID. I only want ID. I don't want any other term. So I move this L to the bottom, W over L, mu N Cox W over L, and then you see VGS minus VTH. So it goes from 0 to VDS. So basically it's only left VDS, okay? Because you know after integration, you will put VDS minus 0, and then you multiply inside the V. So now left only VDS, and then this V left only VDS also. So this become to our final formula for ID. Okay, this is our main formula that you derive. So you finally come in this point, say that, oh, when VGS is more than VTH, when the device is turned on, we will have this characteristic. Your ID will get affected by all these things. So we can draw one ID graph. Okay, you can see there's a square term over here. So basically we will have a top point and then it will maintain. Okay, so we suppose up until now we can only draw ID versus VDS. When VDS increases, so when this point increases, the whole term increases, right? So you can see that it increases exponentially in the curve, go up to this point, and then it will stop. We stop until now first, because now we assume that, oh, this peak time, peak current is somewhere here. Okay, and then if our VGS is lower, what happens? The whole ID drops, right? If our gate voltage is lower, the whole current drops. So that's why we will exhibit this characteristic, the lower characteristic over here. Is everything okay so far? Still with me, huh? I hope so. Because this is the first class. Okay, if okay, then let's just take attendance, and then that's all for today's class.